So we've talked about, the physical changes, chemical changes, the mixtures and alloys and stuff like that. Today, we want to talk about the properties of the atom. We talked about matter, the phases of matter, solid, liquid, gas, plasma, and the difference in all the connections between the particles. Today, we want to talk about the particles themselves. So, the structure of an atom. An atom is the basic, well, it used to be considered the basic building block of all matter. It isn't so much anymore because we found out there are smaller particles in an atom, and yet we found out there's smaller particles than that. Basically, though, our most basic materials, our most basic things, substances, are what we call elements. Depending on what periodic table you look at, there is somewhere between 107 and 114 elements. Realistically, those elements are not all chemically stable. Here, let me pull up periodic table here quick. Maybe. Everything's running slow on our network today. There it is, right there. So, if you pull these up, I'm going to pull up this one here, I think is probably the most. Let's see if any of them has all the, here we go, this is the one I want. The reason I chose this one is because you can see down here it has all these that don't really have a lot of extra information in them. That is because those are, I don't want to say not real, they're synthetic. They do not occur in nature. Of all these other elements, there's one up here, where is it? I believe it's number, it's a hard one to read. Right here, this one here, technetium. This one does not occur naturally. Starting here with honium, those do not occur naturally. In fact, Rutherfordium doesn't really occur very naturally either. Radium does. Actinium is very unstable, but it occurs. Starting about here, 104 on up, they only occur in the laboratory. We can make them in the laboratory. They exist for anywhere from a few seconds down to a fraction of a second before they fall apart and decay. We've never really figured out why technetium does not exist naturally. We can produce it in the lab, and for some reason it's unstable. I have not heard a good answer as to why it's unstable, because you can see, all the elements around it are perfectly stable. These, we know they're unstable because they're just too big. Now this one here, the examercury, there's a belief that that element might actually occur naturally on the planet Mercury. That's why it's called that. Who knows? It's also just below the element mercury too, which I don't know if that has anything to do with their belief or not. But anyway, these are all the elements. But those are all the basic materials. You cannot break them down into other materials that have other properties. They can be broken down into other materials, but they have no distinguishable chemical properties once you break them down. So these are the simplest elements that have their own unique set of properties. And elements are made up of those atoms. The atoms are the basic particles that make up of an element. Now we can combine elements chemically if we combine two or more elements chemically. Now remember we said the difference last week, we can combine them physically in a mixture, or one of the forms of a mixture being a solution or an alloy. They can maintain their own properties in that physical combination. And we can separate them out physically. In a chemical combination, when we combine them chemically, they take on completely new characteristics. We talked about oxygen and hydrogen being two of the more flammable and explosive elements known to man. You combine them chemically, you get water, a substance used to put out fires. A little ironic. Or sodium and chlorine, where sodium is very reactive with water, highly dangerous, highly explosive. Chlorine is one of the more poisonous gases known to man. Actually, chlorine is the main ingredient in mustard gas, which we'll make in the lab some point in the next few weeks. What's that? Oh, just breathe shallow. You've been in the military. You've breathed it in before. Anyway, so you got poisonous gas, a very explosive material. We mix them to make table salt.
That's so good in the burger.
Yeah. So we combine them chemically, we make something called compounds. Well, remember, mechanically, they maintain their original properties. Like salt and water, you mix them together, it's still wet, it can still put out a fire, but you taste it, you can still taste the salt. And you can filter them back out, which is a physical process. No, salt and water would not combine chemically because they don't have the correct molecular structure. Physical combination, you're basically just, mechanical or physical combination, you're basically just mixing them together. Yeah, in a chemical combination, their atomic structures actually combine with each other. Yeah, and only certain things will do that. Yep. So these compounds, which are, again, a mixture of two or more elements, not even a mixture, they're a chemical combination of two or more elements, form what we call molecules. So a molecule is more than one of those atoms linked together. And that would be the smallest building block of a compound. That would be the smallest particle, you could say, that has the characteristics of that compound. So we're going to start today looking at the structure of an atom. We talked about it a little bit in the video we watched last week. But the structure of an atom determines its chemical properties. Now, an atom has two main parts to it. There's three pieces that make it up. There's two main portions or locations of the atom. Atom has a nucleus. I drew it a little bit larger. The nucleus actually takes up very little space in the atom, but has almost all of the mass or the weight of the atom in the nucleus. And then it has what's called electron clouds. You heard that brought up in that video last week. Now, the electron clouds are not really just a cloud with electrons buzzing around everywhere. It actually takes the form of energy levels. This one's a little tough to explain, but basically what it is an atom or an electron moving around the nucleus. It's kind of, think of like a planet orbiting around the sun. You know, the Earth is orbiting around the sun, and it stays in its orbit for two reasons. One, it has adequate mass and velocity to keep it moving at the pace that it's moving in that path. Second, the amount of gravity exerted on it by the sun is the exact correct amount to keep its path bent and keep it going in that path without pulling it in closer or allowing it to drift away further.
So you have one of those effects.
Well, there's some effect of the gravitational force from the other planets, but it's that balancing of forces that allows the Earth to just stay in that orbit because its speed and the forces acting upon it. It's just like taking a ball or a weight and putting it on a string and you spin it around and it spins in a circle. It is spinning in that circle for two reasons. One, its weight and its speed are adequate to hold it in that circle, and two, the string is strong enough to keep it from flying away. Yeah. I mean, if you slow down, it starts to collapse in towards the center. It has to have enough speed and enough weight to keep itself out in the circle. If the string isn't strong enough, that speed and weight will cause it to fly off. So it has to have a balance of that strong enough force, which is the gravity from the sun, and the velocity and the movement. Well, the same thing happens in an atom. You have an electron, it's going to move at a certain speed, and it has to be a certain distance away from the nucleus in order to stay in that stable orbit, you can think of it. It kind of moves. It doesn't necessarily move in a circle around and around, but it kind of moves randomly. And it has its speed that keeps it out at that exact distance, that curvature. Now, there can only be so many of those electrons that fit there. In fact, the first energy shell or energy level, you can only fit two electrons. No more than two can fit in there. They're bumping into each other too much. So what happens then is it has to bump up to a next level. So at this next level, they have to move faster to stay in that level because they got to stay further away from the nucleus. I'll explain why they don't fly off in a minute, what force holds them in there. But this one can hold now up to 8 electrons within that level. In fact, each level after that can hold up to 8 electrons. And so they just keep stacking up. Now you can see nature is inherently lazy. The electrons that are in this lower energy level are moving the slowest. They take the least energy to keep moving. So if it can, the atom is going to put the electrons in that lowest energy level so it doesn't have to use up much energy. But obviously, the more electrons it has, the further it has to push them out. And the further that energy level is away from the nucleus, the more energy it requires to stay there. In fact, we're going to talk a lot about those energy levels as we go on. So we've already talked about those are electrons that are out there in those energy levels. Electrons have a charge of -1. Technically, this is called the -1 electron volt. An electron volt is like 1.602 times 10 to the -23 volts. It is extremely small. Think of 10 to the -23 as a decimal point with 22 zeros and then a 1. That's really small. It has a mass of approximately 0. It's so small it's less than 1/millionth the size of the other parts of the atom. So they're so small they don't even matter. So anyway, in the nucleus then, we have two pieces, protons and neutrons. Protons have an electrical charge of +1. Obviously, you have something that's negative, you have to have something that's positive, so things can be neutral. Again, that's a +1 electron volt. Has a mass defined to be 1 atomic unit. We know it's exactly 1 atomic unit because an atomic unit is defined to be the mass of a proton. So pretty simple. The neutron. Yes. Yeah. The neutron, well, you can already sense it there. Neutron means neutral, has a charge of 0. No charge. It's neutral. Its mass is very, very close to the mass of a proton. So its mass is really, really close to 1 atomic unit. And again, like we said, the electron is like a millionth of that. It's so small it does not matter. Inside the nucleus, we talked about those electrical forces, right? Well, we have the negative electrons out here. We have the positive protons in here. It's the electrical attraction between the positive and negative charges that keeps, it kind of takes the place of gravity when we talked about the orbiting before in the planets. That electrical attraction is what keeps those electrons from flying out. Now you might be asking, if you're a deep thinker, why do those protons stay together? Why don't those repel each other and go flying away from each other? Well, something called the strong nuclear force. Forces come in several different types. What we're going to talk about now is range forces. Those forces that can act over a distance. My hand has no range force. I cannot sit here like this and push Mike away. I have to put my hand on something to actually exert a force on it. It has no range. Well, like magnetism, electrical fields, stuff like that, those have a range. They're range forces. They can act at something from a distance. A positive charge and a negative charge can attract each other from a ways away. Or the north pole of a magnet and the south pole of another magnet will attract each other from a ways away. They have a range. Well, electrical forces have a long range, but relatively weak. Now you might be thinking, I've seen some electromagnets or electrical fields that are extremely powerful. Yeah, that's true. But I'm talking in comparison to the strong nuclear force. The strong nuclear force has an extremely short range. But it has an extremely strong force. So what that means is if I take two protons and I set them like this, they are going to push each other out and they're going to shoot off away from each other. I take two protons and I get them really close together, almost touching. Guess what? That's where that strong nuclear force takes effect and it holds them together. Even though the electrical force is trying to push them apart, once you get them close enough, that strong nuclear force takes over and holds them together. Now, when you get a whole bunch of them in a nucleus, you still have that electrical force. This one here is exerting an electrical force pushing all of the other atoms away, or all the other protons, I should say, away from it, right? Well, this one here is also pushing all of the other protons away from it. If you see, like this one out here is getting pushed by all of them, there is a chance that that electrical force can get large enough to actually overcome, if there's enough protons there, that some of the very edge protons that can overcome the nuclear force and push it away. That is why there are the neutrons. Neutrons are electrically neutral, so they don't have that repulsive force. So if you fill in some neutrons in here, now there are some particles that aren't pushing away. It's putting them further apart, so the electrical field gets weaker as you get further away. But the neutrons, even though they have no electrical charge, still have a strong nuclear force. So they're adding to the nuclear force, and they're actually diluting down the electrical force. So they're keeping those. That's why the neutrons were necessary, is to keep the nucleus together, so that the electrical force didn't build up to the point where the nuclear force could no longer overcome it. So if we go back, I should have kept the periodic table up, I guess. Well, there's a lot of ways it can happen. We talked about a plasma, remember? In a plasma, it gets so superheated that a lot of those forces don't, it's constantly electrically charged. And the forces, some of the main mechanical forces don't act normally anymore. In a plasma, things can come together real easily. Most elements were generated in a star of some sort. Or the Earth itself, when it was hot and molten before it solidified, those elements developed. At this point now on Earth, it is almost impossible to change an atom from one element to another. Because once the Earth solidified, they're pretty much stuck, is that element, that atom, that atomic structure is pretty much stuck. I mean, there are some things we can do to adjust it in the laboratory by literally taking highly sensitive, specialized equipment and pulling little particles off of it. But for the most part, they formed when everything was so superheated that the regular forces didn't matter anymore. It's a deep thought, isn't it? Yeah. So anyway, back to our periodic table here, if I can pull it. In fact, you know what? I'm going to pause for a second. So you have those electron energy shells. The very outer level is called the valence level. And that valence electron energy level is what determines its chemical activity, its chemical reactivity, and all that chemical behavior. In a metal, that outer level is shared around the whole substance. That's why metals conduct electricity and heat and everything else so well. The electricity is just the movement of electrons. Well, if an electron can move from one, if here's my atoms and here's their energy levels, if they have one big energy level going all the way around, if that electron can move from atom to atom however it wants to, electricity can flow really fast. If it can't, let's see, here's my atoms like this, and the energy levels don't move, well, then what has to happen? It doesn't mean it can't conduct electricity, it's just really slow. Let's apply an electrical force right here, right? This electron moves to here, well, it can't go any further. So what has to wait for it to happen is the electrical charge of this electron causes the electrons of this atom to move away. It's kind of a cascade effect. Whereas over here, if I apply an electrical force right here, this electron can go all the way over, all the way as far away as it wants to.
The more electrons it has, the more conductive.
Well, not just the more electrons, but the more loosely the electrons are bonded, the easier the electrons can move from one atom to another, the better it conducts.
So like water's pretty thick conductive then?
Yeah, electricity is movement of electrons. Like you saw up there, those transition metals, the red ones, like aluminum, it's a transition metal. It conducts electricity, but it takes a little bit of force to get the electrons to jump from one atom to another, so it doesn't conduct electricity well. Copper is a full-on metal. Electrons move almost very little force to move them from one atom to the next. Gold is actually an extremely good conductor. The only problem with gold is it's soft and it's expensive. Silver is probably the best conductor of all. Do you know why we don't use? In fact, in some of the luxury vehicles, for the contacts for the airbags, they use gold plating so that they don't corrode. You know what's the aircraft do too? Yeah. And especially some electronics use gold printed tracing. Silver is actually probably the best conductor. Do you know why we don't use silver?
Conspiracy.
No, it tarnishes very, very quickly. So the tarnish, yes. And the tarnish on the surface, pure silver will tarnish really quickly. Most of the stuff that you're familiar with, the silver is called sterling silver, has a small amount of copper mixed in it. But pure silver is extremely conductive, but it tarnishes so fast that it doesn't make contact real well then from piece to piece anymore. With that,
Atoms stay in place while